So I'm here to tell you about secure and privacy-preserving computation, which is an area of cryptography that I have been working on the last 10 years. And I personally think it's going to be very important in the future of our world and society. Because I'm assuming that most of you, if you watch the news over the last several years, this is not an uncommon phenomenon, where you basically have every month or every couple of months a breach that affects you personally, maybe in some cases, of a platform or some back-end database of some system that leaks the information of a lot of people, sometimes in the hundreds of millions. And sometimes you're unwillingly, like that, your information ends up in these databases without your willingness, or you don't have a choice over that. So I assume most of you have had some experience, hopefully not as bad, with such incidents. And what can we do about it? Because, I mean, I personally think this is an unsustainable phenomenon. I mean, are we going to continue like that, where information about us just leaked out there and it's all over the web, basically? So what can we do? Oops. So obviously a lot of governments and nations have started enacting regulations to control this. Europe has the GDPR. Is it a little bit hazy, or is it? It is. Can you control? Yeah, it's very. Anyway, so while he fixes that, maybe I'll. Yes, that's better. Thank you. So Europe, they recently, you might have seen that over the news the last year or so, a lot of regulation over how data of individuals is disclosed, collected, and it puts some restraints on companies, but it's something we have to work with. And in North America, you have similar regulations, especially for sensitive information like healthcare. So the problem was I mean, it's not a problem. We should have these regulations and protect individuals. But the reality is that it hinders the work of systems design. I mean, we all like to have convenience of personalized recommendations. I personally have bought a lot of things online because they were recommended to me based on my previous. I want that, but at the same time, I don't want a lot of information about me to be known to all these entities. So I look at it as a spectrum, where on one side you have utility of using personalized data for recommendation, making my life easier, recommending things that I might be interested in, versus privacy, like what kind of information is leaked about me. And the question that basically, or the one thing that I want you to come out of this talk is, we don't have to give up everything. I mean, there is a technical way, and that's partly because of cryptography, where we can get both. We can have a lot of the utility of using your personal data without actually revealing it. It comes at a cost of more complexity in the algorithms, the software, and overhead in terms of computation and communication, but I just want you to know that there is stuff now that's becoming increasingly practical. And okay, interesting. If basically you walk away with one thing from this talk, is that there's this area of secure computation that if you've ever encountered in your career a problem that needs something like that, that's where you will go and look at. Okay, so one common sort of primitive or sub-area of this is what's called secure multi-party computation. At a high level, what secure multi-party computation allows you to do is basically allow some parties, and using parties here loosely as could be individuals, but the reality is these are going to be machines, algorithms. Allow them to compute a function of each one of them has some input data, and they want to compute a function without revealing what their data is. So like the simplest case would be like 3 people want to compare who is the richest. Why? Because it was invented 30 years at Stanford. That's called the millionaire problem. So can you actually do that? And it turns out yes, and you can generalize that to just more than 2 parties or 3 parties. So the idea is that each party will have its input data, and the computation that they want to compute is well known to all of them. And then they will execute some software over the internet to input basically their data on each of them, not have to send it to a centralized repository, which is the model we have today. They will basically run the software on their data, communicate with each other, and you have mathematical guarantees that you are not going to reveal anything about your input data other than that the function actually reveals. Because if the function simply says, oh, I'm this party, my data is this, I mean, there's nothing I can do. But if the function itself doesn't reveal what your data is, let's say you're computing the average, let's say salaries, average. So over a large data set, you cannot infer what the salary of each one is. Then this becomes very handy. And typically what we'll have is when we design these protocols, you have to assume, okay, what kind of protections are you providing? So typically cryptographers or security people, they work with 2 models. One that's called the semi-honest or the honest but curious. This is a model that mainly cares about privacy. I'm assuming that the software that I will give to each one of the parties is not going to be modified, but they might want to learn a little bit more than what they're supposed to learn. And then there's the fully malicious one, where you don't make any assumptions. Like, you can just go at it. Like, take the software, change the code, try to do whatever you want, and I will have mathematical guarantees that you will not learn anything and you will not affect the correctness of the computation. This typically comes with a caveat that, let's say, if you have 3 parties, that I can tolerate up to maybe less than 1/2 of them. So in the case of 3, I can tolerate one party being completely malicious. And if you're familiar with blockchains and all this, I mean, I view personally this area as a superset of what's happening in blockchain. Blockchain is a very specific case where the function we're trying to do is what's called consensus. Okay, so, and that's basically what I said, that the reality is these are going to be software running on basically virtual machines or actual physical servers or containers these days. Okay, so the blueprint, what I want to tell you about in the rest of the talk is basically how do you actually do that. So you get a little bit of a feeling of what's the underlying technical material, and then you can go and read, and happy to answer questions later. So typically what you will do is you have to encode your data in a way that allows you to do that computation in a distributed way. So, and that's one of the tricks that you're going to like imagine like projecting the data in a domain such that you can compute at it and then reconstruct it, but in that domain, you don't know what the data is. So you will encode that data, and typically it's essentially sharing the data, sort of transforming it in a way that is distributed among the parties. And then the guarantee is that as long as no more than this threshold of parties is corrupted, you cannot figure out what the data is. If you've ever studied error correcting code, it's very similar to what we do for wireless transmission. And then you will compute in this domain in a distributed way, and you will reconstruct then the result of the computation. So yeah, a little bit of math. How would you do this in coding? This is like simple polynomial arithmetic. I mean, if you remember your algebra, any degree t polynomial in a single variable it's uniquely defined by t plus 1 points. So the main idea here is the following. I will take my data, I will come up with a random polynomial of degree t. T here is the number of parties I want to be able to tolerate can misbehave. So if I have n parties, let's say n with 3, and I want to be able to tolerate one party misbehaving, I will construct a quadratic polynomial. My data, for now, think of it as just like a single value. I'll transform it into a number. I'll put it in the free term, okay? And what I get from the math is that if you only have one point on this polynomial, there's nothing. There's an infinite number of polynomials, of quadratic polynomials that go through that point. But if you have 2 or 3 points, then it's uniquely defined. So the idea here is that I will encode my data as numbers, integers, because it's discrete. You have to work with computers, and then you will come up with a random polynomial, and then evaluate that polynomial at the indices of the parties, and then send the evaluation point to each one. And I mean, you can search online for secret sharing implementation. This is not that hard to implement. I want to give you an example of how you would do it in Python. Essentially, all you need to do is just convert your data into integers and then compute polynomials. And the key point is that you always set the free term, which is the intersection with the y-axis, to your data. And then evaluate at different points, and this is basically how you're distributing your data. And to reconstruct, this is also very elementary algebra, is if you have enough points, you can run what's called Lagrange interpolation to recover the polynomial of that degree that passes through these points, and then you evaluate the intersection with the y-axis, set x to 0, and then you get your data. Okay, so that's how you basically encode and decode the information. Now the tricky part, which is the middle part. How do you compute about the data while it's in that form? So luckily, turns out, from theoretical computer science, we know that any kind of computation we need to do, we can represent it as addition and multiplication. Which, when you think about it, this is really what your processor does, right? When your processor it has an ALU, it does addition and multiplication, and has bits. So this already is happening at a lower level. So now we're going to do that at a higher level of the software. So as a developer or as somebody who uses this, I'm teaching it to you, but you're not gonna, like, when you write a program with loops and more complex functions, you're not gonna convert it by hand to additions and multiplication. I mean, this stuff will happen automatically. I'll show you at the end of the talk some open source frameworks that already sort of overload higher functions, but this is what's happening underneath. So you will basically secret share your inputs. That's what these square brackets look like. So each party will secret share input, and then you will compute as a series of additions or multiplications over these secret shared values. And then you will get the result initially in a secret shared value, and then you will reconstruct it. So now what I need to tell you is, like, how do you do each of these gates? So luckily, it turns out that addition is very simple because essentially, if you had two secrets, S1, S2, what happens is, like, think of them as you transform them into polynomials where the values are really encoded as the free term, the intersection with the y-axis. So if you add two polynomials, we'll get a third polynomial that has the same value also at the intersection of the y. So basically, if you have two shares of some secrets and you want to generate the sum of them, just add the two shares. Great. Works without any communication, very little overhead. But life is not that easy because multiplication is not that, I mean, there has to be a catch. So if you try to do the same thing with multiplication, the problem is you'll get a polynomial of double the degree, and if 2t is larger than the number of parties you have, you cannot reconstruct that and you lose it. So what do we do? So there's a trick, luckily. There's actually multiple ways to do this, but this is a simple one that I can convey now to give you the intuition. So the way to do this is we'll assume that before we do the computation, we will distribute some values that are independent of the data and the computation you need to do. And these are basically three values. They're called multiplication triples, A, B, C, such that A and B, select them at randomly and just multiply them, and that's C. And you secret share those three values. So imagine, like, you have three servers coming up to do some computation like this. The first thing is they generate these random values, share them, and then we'll use them in the online phase. And how you use them is basically you will subtract the share of this first value from the first secret, the share of the second value from the second secret, and then reconstruct them. We call these I and K. And then you compute the product, the sharing of the product, as I times K plus IB plus KA plus C. And this works out. I mean, I have it here. You can look at it later. But the intuition is basically things cancel out. All the cross terms will cancel out, and you will be left with the share of the product of the two values. And this is the only catch here is that you require communication when you do the reconstruction. So basically now the blueprint looks like we're doing some pre-processing initially, and then we'll secret share our data, compute over it in this distributed way, and then recover it, okay? So putting it all together, this is something I could, if you want to implement it, I mean, this is complicated when you want it to be performant and fast and scale, but there is value in trying to code it yourself. It's tens of lines of codes if you use something like Charm, which is a Python framework for rapidly prototyping cryptographic protocols, sort of abstracts a lot of the underlying basic math. You would basically have like a share functions, as you see here, it's a couple of lines, and then there's one to add secret shares, and then the multiplication, I'll show that next slide, it's a little bit bigger, and then a reconstruct. This is like the very basic blueprint of that, and you can extend something like this to actually be faster by trying to optimize some things. So the multiplication, it will look something like this. If you assume that you have these triples, you basically, I'm assuming that the shares and the triples are lists that I'm getting, so I'll retrieve each element from them, add with the subtraction that I had, reconstruct, and then do this last step. A straightforward implementation. But the reality is you shouldn't do this because it's very easy to make a mistake and then all the security and privacy guarantees are lost. So luckily there are people working on mature frameworks. So this is one that is based on Python. If you're comfortable with Python, go to this GitHub account, and it's basically a Python-based system called Scale Mamba. It provides you with an interface to program in Python, and it has a runtime that you can run in Docker or VMs, and it has extensive documentation. And it has a lot of functions that you already probably want to do, like adding, multiplying, comparing, already implemented and overloaded so that you just write in Python. And the guarantee is that the computation is actually done in a secure way. So for instance, here, I'm defining it as sint, means like a secret integer. Means that this is never really revealed, only when I reveal it explicitly at the end. So I encourage you to actually go and look at Scale Mamba and play with it. Okay, there's a lot of advanced topics that I haven't covered. We just really scratched the surface. Like, how do you deal with when parties misbehave? Typically, this involves much more complicated cryptography, something called zero knowledge, where in each step, the parties have to prove that they're doing the computation correctly. Scalability, can you scale this to hundreds of parties, even thousands? Large data sets, more complicated functionalities like machine learning, regression. All this is being handled, and we're getting to the point where we're actually, like some of the research literature now shows, you can run it for hundreds of parties on Amazon, AWS, over the world, throughout the world, and actually it performs reasonably well. I mean, you're not going to get real-time performance, but if you're doing batch processing at night of a lot of data, we're there at this point. Other techniques in general in this area, so it turns out the two-party case is a special case. There are other ways to handle it to be more efficient. If you don't want to do a lot of interaction, all you want to do is encrypt your data and compute it with privacy. Use something called fully homomorphic encryption, where you basically encrypt your data, upload it to the cloud, and the cloud can do the computation. You would then decrypt the result. If all you care about is releasing statistics about data sets, use something called differential privacy. I just want you to be aware of these terms, these areas. If you encounter these are the areas to look for if you want to solve problems with privacy in data. So in summary, if you were to walk away from this talk with one thing, is I want you to know that there's a lot of work on technical solutions to the issue of privacy and computing on data, that you don't have to release your data to be able to use it in computation, and that there is a trade-off. And there's an increasing number of frameworks and startups and companies, and big companies are starting to adopt this technology and deploy it even in your cell phone. So like Google, a couple of years ago, deployed an MPC-based solution on Android to do the predictive learning of the keystrokes. Further reading, if you're interested in reading more about MPC, this is a free book that has a lot of the underlying math and protocols. It's a couple hundred pages, but it's written in a very accessible way. This is a collection of tutorials, videos, articles about this area. Again, we just scratched the surface. This is a topic where hundreds of researchers are working on actively, and there's a lot of variations of these protocols. Two mature open source software for MPC. The first one, the Scale Mamba that I talked about, is a Python-based one. If you're more comfortable with Java, there's GIF, which is, you can run it even in your browser to test it. So I think these are two of the most usable ones. I wouldn't be surprised if in the next 3-4 years, like, you have more of these in different languages. And yeah, with that, hope you learned something about secure computation, and I'm happy to take any questions if you have.